Okay, let's talk about nuclear stability. When we talk about nuclear stability, one of the facts is that while we look at something like carbon-12, carbon-13, and carbon-14, carbon-12 and carbon-13 are stable isotopes. Carbon-14 is radioactive. So, how can we understand why these are stable and why these are radioactive? So the first thing we're going to discuss is our neutron to proton ratio. Okay, and when we do that, what we'll see is that we'll be looking at what we call, or what I like to call, is the built of stability. Okay, so let's go put this on. The belt of stability. If you look at the belt of stability, let me get this focus a little bit more. Okay. If we look at the belt of stability, what we find is that this red line on my y-axis is the number of neutrons. On my x-axis is my number of protons. On this line is a 1-to-1 neutron to proton ratio. What we see is in the yellow and the black dots, these are the number of different isotopes that exist for the various elements with the proton number here. When we have basically any of my isotopes, we essentially have the number of protons less than 20. You see that the dark dots here are all my stable isotopes. The yellow ones are all my unstable isotopes. And what we find is that my stable isotopes with the black dots track really well with my 1-to-1 ratio. But once I get to a higher number of protons, where Z is greater, equal to, or greater than 20, we find that the neutron to proton ratio basically increases greater than 1. Part of the reason actually is that, remember, your protons are a positive charge, and to have them all clustered in a small area in your nucleus, you're going to need the strong force to help actually hold your nucleus together. And the neutrons actually contribute to that. They contribute to the strong force, but they don't have a charge for the repulsion from coulombs. So as we increase where the number of protons is 20 or greater, then we see that we have a higher neutron to proton ratio. Just so you know, once we get to the number of protons being greater than 84, greater than 84, all of these isotopes are now radioactive. We don't have any stable isotopes. There is a theoretical island of stability much further out, but we have no elements in that area. So these are all the known elements. So anytime you see this, you're going to say, oh, anytime that your proton is less than, the number is less than 20, then you're going to be looking for stability in a neutron to proton ratio of 1. Now, how do we interpret the rest for the radioactivity? If we look at my stability here, all these stable isotopes, if you are below this line, okay, so let's just pick an isotope right here. Okay, let's say proton number is 50, neutron number is 55. Then what it's telling you is that I don't have enough neutrons in order for me to be stable. So what you need to do is you need to reduce the number of protons and increase the number of neutrons. How do we do that? So remember our basic nuclear equations. We want to reduce the number of protons and we want to increase the number of neutrons. So what we need is we need this. Take my proton and increase it to a neutron. The way we do that is we have a positron emission. Sorry about this. Or you can do an electron capture. Okay? So, given your graph, any of your radioactive isotopes that are found below the dark line, so all these yellow dots here, okay, these guys will basically decay through positron emission or electron capture. What about if you're here above those black lines? What does this mean? Well, let's just take a look here. Let's pick something here. If I have 10 protons, then we're looking at something stable at 10 neutrons. But if I'm above there, then basically I have too many neutrons and too few protons. So if I'm above my graph, then what I need to do is take my neutron and convert it to a proton. You'll move it here and reduce this number down, and you'll get closer to the stable isotope. So anything above my belt of stability, you'd undergo a beta emission. Because remember, if I did a beta emission, I'll use that with a blue pen, just so you know. So this is below the belt of the stability, belt of stability. Okay, and this is above the belt. So when you're above the belt, you have too many neutrons and too few protons. So what you do is you want to convert your neutrons to a proton. And to do this, you need a beta emission. So you're emitting a beta particle. Okay? What happens? So now that we know from your graph what happens above the belt, beta emission, what happens below the belt, that's either positron emission or electron capture, what happens way up here where everything is radioactive. When you're way up here, you have too many protons and too many neutrons. So when you have Z greater than 84, all of these isotopes lose an alpha particle. Okay. So, you get an alpha decay. You lose 2 protons and 2 neutrons. Okay? So, when you are in the range right here, where Z is greater than or equal to 84, to bring it down, you need to lose both protons neutrons go down and protons, and you'll go left, okay, to get to the belt of stability. What other ways, besides looking at the belt of stability, can we discuss actually nuclear stability? So knowing how to interpret your graph is essential. The other thing is we're going to also look at magic numbers. And I highly recommend looking at this YouTube video that describes how we get our magic numbers. www.youtube.com, and it's watch V equals 8V capital M W Z K capital O I 0 V4, and he explains where the magic numbers comes from. So it has to do basically just like electrons have their electron shells with a specific order, nucleons also have a specific order and shells, and he describes how you get your quantum numbers for that and how that actually adds up to your magic numbers. So when you look at your magic numbers, and this applies to protons and neutrons, okay? So if you have protons that actually have these magic numbers, you'll see stability. If you have neutrons that have this magic number, you also see stability. If both your protons and neutrons have these magic numbers in the nuclei, then you see an extra stability with them. So the first one is 2. The second one, which is the sum of 2 shells, the first and the second, which actually contains 6, is 8. The third magic number, which contains the 2 and the 8, and the third shell contains up to 12 nucleons, gives you a total of 20. Okay? And so you get 28, you get 50, and if you continue, you'll see 82 and 126. Now we know these apply to protons and neutrons. And this one applies to your neutrons, because as you know, any number of protons greater than or equal to 84 is automatically unstable. So you need to know these magic numbers. And if you want to do the analogy, let's give you an analogy. If we look at our electron shells, remember, row 1 contains only 2 electrons. Row 2, basically we have 8 electrons. We have basically the 1s2, but then we have 2s2, 2p6. So for row 2, the total number of electrons is up to 10. Okay? The total number of electrons from our first, second, and third rows is 18. And for row 4, we have up to 36. Okay? Etc. So just like we sum up the electrons, total electrons, okay? We're summing up the total of nucleons here. And these magic numbers indicate a particular stability in the nucleus if you have these numbers. The last part for our nuclear stability we're going to talk about would be the number of protons and the number of neutrons. So if you just look at the number of protons and the number of neutrons, if the number of protons is even and the number of neutrons is even, okay, basically we get 157 of all our isotopes that are stable. Okay, so most of the protons and neutrons, when they are even and even, they're going to be stable. The number of stable nuclides that have an even number of protons but an odd number of neutrons, that's 53. Let me just put this a little further out so we don't confuse them. Okay. (157), 53. If I have an odd number of protons but an even number of neutrons, I still get 50 stable isotopes. It's only when you get to the odd number of protons and odd number of neutrons that we only encounter that there, of all of the isotopes that have an odd and an odd number, only 5 are stable. So the likelihood then of having a stable isotope with an odd number of protons and an odd number of neutrons is extremely low. So when we talk about stability of the nucleus, we can look at our belt of stability at the graph and determine what kind of decay will occur. We can also look at our magic numbers. That gives us an indication about the stability of the nuclei that we're looking at. And also, in terms of the number of protons and the number of neutrons, if anything, if you see an odd number of protons and an odd number of neutrons, that's probably going to be a radioactive isotope.